Scientists at the European Organization for Nuclear Research recently watched a specific particle decay and saw a massive portion of its energy simply vanish into thin air. How can we be certain that energy is actually gone if we cannot see where it went or what took it away? In the first 60 words of this video, I am going to answer the question of how CERN watched a charged kaon decay and why part of its energy disappeared completely. And I will show you the exact evidence that confirms our current laws of physics are still standing. We are looking at a process so rare that it happens to fewer than 1 in 10 billion particles, yet we have now measured it with enough precision to prove that the missing pieces are exactly what our math predicted they would be. This is not a story of a mistake or a leak in a tank, but a deliberate hunt for the most antisocial particles in the universe, using a machine nicknamed the Kaon Factory. By the end of this video, you will understand how we measure the invisible and why this disappearing act is the ultimate test of everything we know about matter. To see this energy vanish, we first have to look at the standard way we think the world works. In the old model of physics, every time a particle breaks apart, we expect to be able to add up all the pieces and get the same total we started with. If a heavy particle turns into lighter ones, the leftover energy should show up as light or heat or motion that our sensors can easily pick up. When scientists see a gap in that math, the first reaction is usually to assume the equipment missed something, or that a common particle simply flew out of the detector without being noticed. We usually dismiss these contradictions as background noise, because the universe is a messy place, and sensors are never perfect. However, at the European Organization for Nuclear Research, a project called the North Area 62 experiment was built specifically to ensure that nothing is missed. They use a beam of protons moving at 400 gigaelectronvolts to smash into a target and create a stream of billions of particles. Among these is the charged kaon, a tiny bit of matter that only lives for a fraction of a second before it falls apart. The strange measurement that started this investigation was a specific type of decay where a kaon turns into a pion, but the math for the energy and momentum simply did not add up. If you imagine a firework exploding and only one spark flies out while the rest of the explosion stays dark and silent, you have an idea of how strange this looks to a particle physicist. The reason this specific disappearing act is so important is that it is theoretically clean. In most of physics, the math is so complicated that we are not quite sure what the answer should be. But for the charged kaon, the standard model gives us a very precise number. It says that for every 10 billion kaons, only a tiny handful should decay into a pion and 2 neutrinos. Because neutrinos are famous for passing through solid lead as if it were empty space, they never leave a mark on the detector. The energy they carry away is essentially stolen from our view. This creates a missing mass signature that is the primary clue for the experiment. To find this needle in a haystack, the team at the North Area 62 experiment has to filter through nearly 1 billion particles every single second. Only about 6% of these are the charged kaons they actually want to study. They use a giant vacuum tank that is over 60 meters long to give these particles a clear path to decay without hitting any air molecules. If a kaon hits an air molecule, it creates a fake signal that looks like missing energy, but it is actually just a collision. By working in a vacuum, they ensure that the only thing that can cause energy to vanish is the internal laws of the particle itself. This setup is a masterpiece of engineering designed to eliminate every possible excuse for a measurement error. One of the most critical tools in this hunt is a system of trackers and spectrometers that measure the exact path and speed of the incoming kaon. Before the particle even enters the decay tank, the machines know its momentum with extreme precision. They use a special type of detector called a Cherenkov counter to identify the kaon by the specific ring of light it produces as it moves faster than light does in that medium. This allows the scientists to separate the kaons from the much more common pions that are also in the beam. If they cannot identify the starting particle perfectly, they can never be sure that the energy disappearance at the end is real. Once the kaon enters the long vacuum tube and decays, the experiment looks for a single outgoing pion. This is where the detective work becomes intense, because they have to prove that nothing else came out. They use a hermetic photon veto system, which is essentially a series of high-precision light sensors that surround the entire decay area. If any other particle, like a photon or a neutral pion, is produced during the decay, these sensors will catch it. The timing on these sensors is better than 100 picoseconds, which is a tenth of a billionth of a second. This level of speed is necessary to make sure the single pion they see actually belongs to the specific kaon that just passed through. The core contradiction that the experiment has to resolve is why the energy vanishes in such a specific way. When the kaon turns into a pion and two neutrinos, the pion carries away a certain amount of momentum. By subtracting the pion's energy from the original kaon's energy, the scientists calculate what they call the squared missing mass. If this number falls into a very specific range, it proves that two invisible neutrinos were created. If the number is wrong, it means they are just looking at a common decay that they failed to measure correctly. This micro-reframe changes the way we look at empty space in a detector. The absence of a signal becomes the most valuable data point they have. To reach a definitive conclusion, the team had to collect data for years. In the world of particle physics, you cannot claim a discovery until you reach a statistical threshold called 5 sigma. This means there is less than a 1 in 3.5 million chance that the result is just a lucky fluke. In 2024, the North Area 62 collaboration officially announced they had reached this gold standard. They had seen enough disappearing energy events to confirm that this rare decay is real, and that it happens at the frequency predicted by our best theories. This was a massive win for the Standard Model, which is the guidebook we use to understand the subatomic world. However, the story did not end there, because the researchers wanted to know if there was any hidden physics hiding in the margins. Between 24 and 26, the experiment received a significant boost. They upgraded the hardware to handle a beam intensity that was 30% higher than before. This allowed them to harvest more data in a shorter amount of time, but it also created a problem. More particles mean more noise. To solve this, they turned to advanced machine learning techniques. These artificial intelligence algorithms were trained to recognize the signature of a true neutrino event and separate it from the chaotic background of a billion particles per second. This digital filter was so effective that it cut the uncertainty of their measurement by 40%. The precision of the measurement is now truly staggering. The team found that the branching ratio, which is the probability of this specific decay happening, is approximately 9.6 times 10 to the negative 11th power. In plain language, that means out of every trillion kaons, only about 96 of them will perform this specific disappearing act. This number matches the theoretical prediction of the Standard Model almost perfectly. While some physicists were hoping to find a discrepancy that would point toward new forces or dark matter particles, the fact that the result is so close to the prediction is a profound confirmation of our current understanding. It effectively closes the door on several fringe theories that suggested other invisible things might be stealing that energy. Every time we confirm a measurement like this, we are testing the limits of human technology. The North Area 62 experiment is essentially a giant scale that can weigh things we cannot see. By proving that the missing energy is exactly what we expected, we are confirming that the invisible part of our universe follows the same strict rules as the visible part. This creates a sense of reverence for the hidden machinery of nature. Even when something seems to vanish, it is still accounted for in the ledger of physics. The missing energy is not a mystery anymore. It is a signature of the neutrinos that are constantly streaming through us without our knowledge. To answer the title question directly, CERN watched a charged kaon decay and part of its energy disappeared because the kaon transformed into a pion and two neutrinos. The neutrinos are the reason the energy vanished from our detectors, as they do not interact with ordinary matter. The evidence from the North Area 62 experiment eliminates the possibility that this energy loss was a measurement error or a common decay. It also eliminates several theories of new physics that predicted a different amount of missing energy. The mechanism that remains strongest is the standard model of particle physics, which predicted this exact result with incredible accuracy. While the mystery of why the universe is built this way remains open, the mystery of where that specific energy went is now resolved. This verdict changes how we view the progress of science. Often we are told that the most exciting thing in physics is finding something that breaks the rules. But there is a different kind of power in finding that the rules hold up even under the most extreme scrutiny. By measuring one of the rarest events in the known universe and finding that it behaves exactly as predicted, we have confirmed that our map of the subatomic world is incredibly accurate. It tells us that we are on the right track and that the tools we have built, from the 400 gigaelectronvolt proton beam to the 100 picosecond timers, are capable of touching the very fabric of reality. The precision we have achieved here is a testament to what happens when we refuse to accept a gap in our math. We did not just wonder where the energy went. We built a 60-meter vacuum tank and a billion particle per second filter to go and find it. As the North Area 62 experiment continues to collect even more data, the window for finding new physics in this specific decay is getting smaller. But that smallness is where the next generation of discoveries will live. We are now looking for even tinier deviations, the kind that might finally explain why there is more matter than antimatter, or what dark matter is actually made of. For now, the charged kaon has given up its secrets, and the energy that vanished has been tracked down to the last trillionth of a joule. It is a reminder that in the universe, nothing is ever truly lost. It is only hidden from those who do not have the right tools to look for it. If you found this dive into the invisible world of particles fascinating, consider following the journey as we continue to explore the deepest reaches of physics. The work at CERN is far from over, and every billionth of a second, more particles are telling us the story of how everything began and how it all stays together.